So we are continuing chapter 15, I think, and we started talking about Ksp. So I think that sounds about right. A reminder, Ksp is the solubility product. It really is just an equilibrium constant that is typically an equilibrium constant for things that are, for the most part, insoluble. So kind of based on solubility rules, these are the things that we normally think about as being solids, insoluble. And it creates a common situation when we're dealing with Ksp, which is when we look at sort of the equation that we write, pretty much 100% of the time on the left-hand side there, those guys is pretty much just going to be a solid. And on the right-hand side is really where we have our aqueous ions on this side. And because this is normally always the sort of setup for a Ksp problem, when we do write our Ksp, which is just the equilibrium expression, it is pretty much just our product. So it's usually just our product side here with our positive ion and our negative ion, and really just the products. Really no sort of reactants usually involved in the Ksp sort of calculation. We typically can solve this one of two ways. You could really use an ice table no matter what type of problem you're doing. But we do an ice table like normal, where we have our solid going to our aqueous ions on the product side. The difference is, though, we typically will oftentimes use a different letter for the change part. We oftentimes will use like S for the change part. We still do it based on the coefficient, and obviously we would put those in like we would do 2x, we would do 2s or something of that nature. And what that S does stand for is the molar solubility of a compound, which is basically the molarity, right, which is our moles per liter. So when you do solve for S in this case, that is, again, typically our molar solubility. We oftentimes will also maybe want the solubility in something like grams per liter or some other unit sort of given like that, where we can go from obviously moles per liter to grams per liter using the molar mass of the compound to go and do that conversion. There's really kind of two types of problems. One is where you're given the Ksp, and that's pretty much all you're given. That usually does require you for sure to do an ice table. The other sort of problem is you're actually given the solubility of the compound. And again, that could be in grams per liter, some other unit. It could be moles per liter, which would be the molar solubility. So whatever you're given, you pretty much want to find the molar solubility, or S there, of the ions that are present. And then really you just go into the Ksp sort of formula and actually solve for the Ksp. So this is the second type of problem we commonly come across, is you're actually looking for the Ksp and you're given something about the solubility of the compound. You could get them into their sort of molarity of each of the ions and actually calculate the Ksp, and the opposite of that is you're just given the Ksp. You need to do an ice table to solve that. I think we did one or saw one earlier before we left where you can even still do an ice table for the bottom one there. And sometimes it's good because people oftentimes in these problems get a little confused, especially if they come through the table here and they actually have like a 2 or something there. And they sometimes go, well, I kind of multiply by 2. And then when they go to the Ksp, they're all, do I need to still square it and stuff like that. So sometimes if you kind of do the ice table, even though you don't necessarily need it, it'll kind of allow you to probably do the calculation part sort of correctly as well. Any questions on any of that stuff there? Okay. Sounds somewhat familiar, I hope-ish. Yeah. All right. So why don't you do, what is the solubility of silver chloride here in grams per liter? And there's the Ksp of it. Okay, let's take a look, see how you're doing. So this is a problem where, again, really the only thing given to us is the Ksp. So we definitely should do an ice table in this case. So initially here, we would have 0 of our ions. We would assume that it's obviously going to the product side, so that will be plus S and plus S here. That means at equilibrium, we would get S and S. As we might have talked about before, this is a solid, not going to be included in anything, so best not to put anything there that you might try to use wrongly there in the future. Any questions on the sort of the ice table here? This, like a normal sort of ice table, will now go into our equilibrium expression, which is our Ksp. And in this case, it would be the concentration of silver times the concentration of chloride, and it would equal 1.6 times 10 to the minus 10. Putting our s's in there gives us s squared is equal to 1.6 times 10 to the minus 10. Do a little square root action of both sides there, gives us a number which is 1.6 exponent minus 10. Looks like we'll call it 1.3 times 10 to the minus 5. This would be the molar solubility, would be S, right? Which is the technically concentration of chloride at equilibrium. It is also technically the concentration of silver ions floating around that solution. And if we work our way backwards, it is a 1-to-1 relationship between either one of those, which means that is also the molar solubility of silver chloride here as well. Any questions on that there? That is the molar solubility here, which is moles per liter, but that is, again, not what we're really looking for. We are looking for how many grams per liter it is. So basically, we got 1.3 times 10 to the minus 5 moles per liter of silver chloride. We would need the molar mass here to do our conversion. So that is 107.9 plus a 3545. Looks like a 143.4 grams per mole. We will use that as our conversion factor here. We're going to put the grams on top because that is where we want it. Grams per mole. The moles cancel, leaves us with, we'll call it 1.9 times 10 to the minus 3 grams per liter. First off, any questions on that calculation there? Is this very soluble? This is not very soluble. Basically, what that number means is you could dissolve a whopping 0.00 like 19 grams of silver chloride in 1 liter of solution, or 1,000 milliliters. That is not very much. Yes, 1,000 milliliters is a good amount of volume, and you could only get about 0.002 grams to actually dissolve in there. This also brings up the point that we talked about, I think, the other day as well, is even though we technically think of things in terms of solubility rules as being always insoluble, even something that is technically insoluble has some degree of solubility, as you can see here, very, very small, but some of it is going to basically dissolve into ions, even though technically, based on solubility rules, we think of it as being 100% insoluble, but there is still some of it breaking apart. Any questions on that calculation there? Okay. Yeah. Right. So usually if they don't sort of specify, they usually will specify in problems, in terms of the units that you want, unless they say it in words like molar solubility, and obviously that means molarity. A lot of times if they just straight up say solubility, oftentimes they are looking usually for grams per liter, but definitely on an exam or quiz, it will be specified what units you should be end up with. Yep. Other questions? Okay. Then let's try one more here. Calculate the concentration of aluminum in a saturated solution of aluminum hydroxide. The Ksp is 2 times 10 to the minus 32 in this case. See what you come up with. Okay, let's take a look at this one. So again, we probably want to start with a nice table. We're really only given, once again here, the Ksp. So we'll do our equations. So because this guy has a Ksp, by the way, we pretty much know that's going to be the solid, just so you know, kind of like K's go with weak acids, Kb goes with that. You see a Ksp, probably that guy there is going to be a solid. is going to break apart into its ions, which should produce us a aluminum there. And we should get a few of these hydroxides here also produced. Now we'll approach the same way here. This is going to once again be 0 and 0. Our change here will be plus S. And now we do have a coefficient there, so that's why it's important to break it apart correctly. We do need the 3 there for the coefficient like normal. That will then bring us to our equilibrium here, which will be S and 3S. Any questions on that there? This will go into our Ksp expression, which in this case is the concentration of aluminum times the concentration of hydroxide. And we also need to remember, because of that 3, we do also need a cubit here as well. So again, this is what I was talking about earlier. Sometimes people go, well, I did the 3 here, I still need a cubit, and they sometimes will leave out one of those those steps there. I spit that out as I'm talking here. All right, so we're going to throw those things in there. That's going to give us S times 3S, which is going to be cubed, is equal to our 2 times 10 to the minus 32. Doing some cubing of both things in the parentheses, which is very commonly missed by people, does give us 27 S to the 4th. And that 27 comes from 3 times 3 times 3, which is very commonly not done by people. They just square or cube the S, not the actual number that is there. And that would equal our 2 times 10 to the minus 32. We're going to send the 27 over to that side. And that will get us S to the 4th is equal to like 7.41 times 10 to the minus 34. This is the 4th root action we need to do here. Yes, on both sides. That's going to give us an S. And by the way, if you're not sure how to do that on your calculator, you take the number you got, you could hit the caret, do a parentheses, 1 divided by 4. We'll do that for you if you're not sure how to do that. If you don't have one of those buttons, you can obviously use that button as well. But again, if you caret it, or some calculators like this one or the other one there has like a Y to the X type button, you could do that basically in parentheses. 1 over 4 is the 4th root, 1 over 3 is the cube root, 1 over 2 is the square root, and so forth. So however way you want to punch that into your calculator, I'm going to caret it here on this calculator and do a 1 divided by 4 to do that for me, because I don't have any of those fancy buttons. That is going to give me a 5.2 times 10 to the minus 9. That would be our, obviously, if we look at our table here, that is what the aluminum would equal. And that would be the concentration of aluminum. If your calculator is not in scientific notation, you might have a bunch of zeros and a 5 at the end if it kind of ran out of room. And that would be obviously the same deal. Or you could turn it into scientific notation. That's where the 2 comes from. First off, any questions on that there? Now, you know, it didn't ask for it, but if I wanted the concentration of hydroxide here at equilibrium, what should I do? Yeah, again, here hydroxide would actually be 3S, so we would need to multiply it if we were, and again, it didn't ask for it, obviously, but in this case, it would be 3S, which in this particular case would get us, times that by 3, like a 1.6, if you will, times 10 to the minus 8 molar. This, again, the S that you get is actually still the molar solubility of the whole thing. Yes, sir. You probably should. But I don't know. I felt like that's a little bit much on this one. Yeah, but technically speaking, the only one that's there really is 1 sig fig, but I obviously didn't do that. But yeah, it technically should be. Which then would be obviously 5 to the 9, and then that guy would actually probably maybe round up to 2. Now, that S that we get is technically, like I said, the solubility of this guy. When you do solve for S, it really is the solubility of the whole thing. You may be asking, I have 2 different numbers here. How does that work out? It works out because when we look at aluminum, it's a 1-to-1 relationship, which gives us the same number. When we look at hydroxide, it's a 1 to 3 relationship. So we actually would divide the 3 out, going back to the other side, and it puts us back basically to S. So it works out the same no matter which one you look at in terms of that. So whenever you solve for S, it really is, kind of that molar solubility of the whole entire thing. In this case, we were looking for the molar solubility. If we needed, obviously, grams per liter. If we were interested in just the aluminum, we would want to use just the molar mass of the aluminum, right? And if we were interested in hydroxide, we would want to use the molar mass of the hydroxide. Or if we're interested in the whole thing, we'd obviously want to use the molar mass of the whole thing. So you want to make sure you read the question carefully. Sometimes they're interested in the ions, sometimes the whole thing. Make sure to get the correct molar mass if you need it. Other questions on that here, these type of problems? Okay. So let's talk about actually using Ksp values to help us decide, which one is more soluble, which one is least soluble. So there are a couple of situations where you would use the Ksp value, and actually there's one situation where you could use the Ksp value, and there's a situation where you should not use the Ksp values to do that. First off, if you are trying to compare the solubility of ions that are compounds that break apart into the same number of ions, then you can use the Ksp values to help you determine which one's going to be more soluble. So these 3 examples here, if we took each of these guys, this would be silver iodide, which would break apart into silver and iodide. That is a grand total of 2 ions present on the right-hand side. Copper 1 iodide would break apart into a copper 1 ion plus an iodide ion. That also would be 2 ions. And our calcium sulfate here, when it would break apart, will give you a calcium ion and a sulfate ion. Because these guys pretty much break apart into the exact same number of ions, if you basically did an ice table for these guys individually to figure out the molar solubility, they all would end up as S and S. So S squared equals the Ksp in each of these cases is what they would all end up being, which means you actually don't need to do the ice table because you could actually just use the Ksp values in this case to help you decide. The Ksp value, that is the larger one here, would mean when I reach equilibrium, do I have reactants or products? Mainly. Large K value means reactants or products. Yeah, remember Ksp is just a K value, right? So a large K value, large Ksp value means you mainly have products. And since pretty much all these are this equation here, which is solid goes to aqueous ions, if I have a larger Ksp, that means I have more products, which means I have more ions, which means the only way to get ions is for that thing to be more soluble, right? If you have a smaller Ksp, you would have obviously more reactants at equilibrium. And a smaller Ksp would mean more reactants, less ions floating around, which means it did not really dissolve or break apart as much, and it is actually less soluble. So the one situation where if you're asked, hey, which one of these will actually precipitate out first, and they actually do break apart into the same number of ions, you could look at the Ksp value. The one with the larger one will stay in solution longer. The one with the smaller Ksp will come out of solution and precipitate out faster. Any questions on that? So if we actually did compare the Ksp values in this case, we would see calcium sulfate actually has the larger Ksp value, while silver iodide would have the smaller Ksp value in this case. Question on that? Again, you could only do a direct comparison if what you are comparing both breaks apart into the same number of ions. What happens if they don't break apart into the same number of ions? So if we take a look at this guy here, that is copper 2 sulfide. That gives you a copper 2 and a sulfide. That is 2 ions. That is silver sulfide, which gives you a couple of silvers plus a sulfide. That is 3 ions. And that is a lot of ions. Gives you 2 bismuths and 3 sulfides. That's like 5. Now, you might be tempted to do the same thing and look up the values for each of those in a table and go, all right, based on the Ksp values, this guy has a larger Ksp, right? This guy has the smaller Ksp. We would expect this guy to be more soluble and this guy to be the least soluble. When you actually go through and do a calculation like we were doing with an ice table, what you actually see is the molar solubility of this guy is actually a lot less than the molar solubility of this guy. 10 to the minus 15 is a larger number than 10 to the minus 23. A reminder, with a negative exponent, that is to the left there with zeros, right? So the smaller negative number is the larger. So what we actually see when we work it out is it's actually this guy here is actually the most soluble, and this guy here is actually the least soluble. And that's because when we get to the ice table, you got things like s squared for the first guy, you got like, 4s cubed for the second guy, you got some different sort of calculations going on based on the number of ions that are present. So in a situation, if you're trying to compare which one you would expect to perhaps precipitate out first or stay in solution longer, and they do not break apart into the same number of ions, you got to kind of do the whole calculation for each of them individually, and then you can compare the molar solubility that you get for each of them and make that determination. Any questions on that there? So same number of ions, you're good to go. You can look at the Ksp, different number of ions, you got to actually do the calculation. All right, any questions on that? So we oftentimes think about, as I said before, sort of solubility rules as being 100% correct 100% of the time, which means if I look on my little solubility table, which they made you learn, they made you learn those, I know. I didn't even make you learn those, I don't think. So when you look at it and it says, hey, this thing's going to be insoluble, we think it's 100% time always going to be insoluble. But there's a lot of things that do affect solubility. We're going to talk about a few things here that actually can affect the solubility. It can affect whether or not you actually do see perhaps the solid being formed or you don't see the solid being formed. One thing that we're going to look at is the common ion effect in solubility. So the common ion effect is what we've talked about with buffers, right? It has obviously a common ion that is present there. The presence of a common ion when we talked about buffers is that it will keep the weak acid or weak base basically together, right? Not as much coming apart, and it will suppress it. The same thing happens when we talk about solubility. Again, if you just think about the basic type of reaction that occurs here, solid on the left, aqueous ions on the right, which means the only place we could possibly have a common ion would be on the product side, which means we would be adding more product. And based on Le Chatelier's principle, if we add more product, it should shift which way? It should shift to the left there, right? And it will cause that equilibrium to shift to the left, which is the solid, thus meaning not much is going to dissolve, right? We're going to actually decrease the solubility of that salt. It's going to be less soluble in that case because it's being pushed back together, basically, based on Le Chatelier's principle. And we can see that if we look at an example like silver bromide, for example. If we look at silver bromide, which has a Ksp value here of 7.7 times 10 to the minus 13. If we do our ice table here and our calculation, we get some silver, we got some bromide. And again, this is going to be 0 and 0, plus S, which means at equilibrium here, we got S and S. Going into our Ksp, which is our silver times our bromide, will give us S squared is equal to 7.7 times 10 to the minus 13. We're going to square root both sides, and that will give us a molar solubility here for silver bromide of the square root 7.7 minus, I'm not sure what that symbol means, I just hit there, minus 13. And we got something like, we'll go with 8.8, I think, times 10 to the minus 7 molar. So that would be the molar solubility basically of silver bromide in water. Which for reference sake is roughly 0.00016 grams per liter, basically. Again, a very small amount. Now, what happens though if we kind of throw this guy into a solution that also contains sodium bromide? So if we do that, the sodium bromide, which is a salt, will break apart into a sodium ion and a bromide ion here. And our common ion in this case would be the sodium or bromide. It would be the bromide. So let's see how that will essentially affect our ice table here. We will go this way, I think. There we go. We got our silver bromide going into our silver and our bromide. Now, the effect on sort of the ice table is we are zeroed here for our silver, but we do have some bromide being contributed from the sodium bromide that's in the solution. It is a one-to-one relationship between sodium bromide and the bromide ion, which means we should have an initial concentration on the right-hand side of 0.001. Again, very similar to sort of buffers. If you're going to do an ice table, you got to have a number there on the right-hand side. The rest of the ice table is going to be identical, so plus S and plus S, which means we end up with S and 0.001 plus S. Any questions on that so far here? Now, how do we go about solving this? We solve it the same way. We're going to put that into our Ksp expression. So that will give us S times 0.001 plus S will equal our 7.7 times 10 to the minus 13. Well, frankly, I don't feel like doing any quadratic. I don't know about you, and that is a super small K value, right? So just like we did with X's, you could actually assume that S is equal to 0. Just like in the X's, we can't get rid of all of them, right? So it is still the only one that in this case you would be adding to. So we get rid of that guy. That would then give me S times 0.01 is equal to 7.7 times 10 to the minus 13. We're going to divide, obviously, that to the other side, and that will get us I feel like I lost a 0 there. One more 0. There we go. Do that. There we go. Looks like a S of 7.7 times 10 to the minus 10 molar. Just like normal, you should give it a check, but I'll be honest with you, in most cases, you should be good because these values are fairly small, and we're not having a lot coming off to begin with anyway. So never hurts to check. There could be a rare situation where it might not work, but most cases you'll probably be okay. So the check is actually good here. Like I said, you're nowhere even near 100 or 1%. But this would again now be the molar solubility of silver bromide in a solution that also contains sodium bromide. And when we look at the solubility of the two, which one is more soluble? It is the solution in water, right? 10 to the minus 7 is a larger number than 10 to the minus 10. And we see basically the Le Chatelier's principal effect here because of the presence of that initial amount of bromide, going to cause the equilibrium to shift this way, keeping more of this guy together and decreasing the solubility, which obviously we can see when we look at the numbers where it was just water and nothing else was in there with it. Any questions on that? So one way that you obviously can affect the solubility of something is to have the presence of a common ion. The way it usually will affect it is actually making it less soluble than it would be in just pure water. Any questions on that? All right, then why don't you try one, a little silver chromate, I think they call that. What would be the solubility of this compound in a solution that already has potassium chromate? Why don't we do molar solubility here is good. So molarity. Okay, let's take a look. So again, if you're not sure, you got a couple of things mentioned there. We do see the Ksp is associated with this guy. So again, that is going to be the one that's going to really set up the equilibrium. So that's a good place to start. So that's a little silver chromate, I think. And that means we know this guy will be a solid since I see a Ksp value that will break apart into a couple of silvers in this case, and one chromate that has a -2 charge. That obviously will equal our Ksp value we got up there of 9 times 10 to the -12. We also have potassium chromate, which is K2CrO4, potassium being +1 and chromate being -2, which is again why we need 2 of them. It will break apart, since it's sort of an electrolyte here and a salt, into a couple of potassiums and a chromate in this case here. Obviously, it is the chromate that is going to be our common ion. Any questions up to there? All right, so really the main difference, as we saw, is this guy is 0.1. And obviously it is a 1-to-1 relationship here between those two, which means we could roll with the same concentration for that guy. Again, here, if we wanted the potassium's concentration, we would have to multiply it by 2 because of the coefficient, not needed in this problem. So initially we will have 0. And again, the main important part here is we do need that initial concentration for that guy. Otherwise, we're basically doing it in water and you'll get a different answer. Chain is going to be plus, also important here, a 2s there because of the 2, and a plus s for that guy, bringing us to a 2s and a 0.1 plus s here. Any questions on the ice table? Going to go into our Ksp expression here, which will be silver. Also important, the coefficient there is we do still need to square it. And we do need to multiply it by this guy's concentration. Substituting our numbers in there, that gives us a 2s that does need to be squared. And that will give us a 0.1 plus s. And that will equal our 9 times 10 to the -12. Just like we did on the previous problem here, I'm going to assume that s is equal to 0. And again, it is really just this s right here. We don't touch, obviously, the other s on there. That will reduce us down, and squaring it to 4s squared there times 0.1 is equal to 9 times 10 to the -12. At this point, you can do whatever you like there. You can take the 4 times the 0.1, then divide it, which might be a good idea. So we'll take 9 to the -12, that is positive 12. Let's try -12. And we're going to divide it by basically 4 times 0.1, right? And that's going to get us a s squared value here, because I haven't square rooted it yet, of 2.25 times 10 to the -11. And that is what is left, which is to actually square root it. And if I square root that guy here, gives me a, I'll just go up on top so it might be easier to see. S is going to be, after the square root, 4.7 times 10 to the -6 molar here. And that would again be the molar solubility of this guy here. Again, if we put it back into here, we would times it by 2, but then going backwards to the other side, we got to divide the 2 back out. So again, it becomes S basically. And same thing over here. We could check our assumption, again, taking that and dividing it by 0.1 times it by 100. And again, you should be okay in this particular case. If we wanted grams per liter, we would use the molar mass, obviously, of this silver chromate to figure out how many grams per liter that would be. Any questions on that calculation there? Question on common ion calculations involving solubility. The overwhelming thing that happens is it basically decreases the solubility of that salt. Any questions on that? Okay, so that is obviously one thing that really does affect the solubility of a compound. Another really important thing that affects solubility is pH, hence why a lot of the instructions, like in the experiments we're going to do today, and we did before, those qualitative analysis ones, they have you like, you know, add some acid, then add some base, and add some more acid after you did it before. And again, playing with the pH can affect the solubility of certain compounds, especially sort of acids and bases. The presence of a common ion, as we just saw, does decrease the solubility. When we have insoluble bases, they typically will dissolve in acidic solutions. And if we have insoluble acids, they typically will dissolve in basic solutions. So if we take a look at, say, this example here, which is magnesium hydroxide, it would break apart into magnesium ions and a couple of hydroxide. That would give us a Ksp as we see down here. And if we went through our table here, this would be 0 and 0. This would be plus S and plus 2S, which means at equilibrium here we would have S and 2S. This would go into our Ksp expression here, and that will give us S times 2S, that does need to be squared, is equal to 1.2 times 10 to the minus 11. Doing a little math in my head there, we'll hope for the best. That is going to give us a 4S cubed, I hope, is 1.2 times 10 to the minus 11. We're going to divide the 4 to the other side and do a little cubed root action on that. And that is going to be 1.2 to the minus 11 divided by 4. And again, take your cubed root. You can do the caret, and 1 divided by 3 will work for you if you don't have that button. And that will get you an S value here of, we'll call it 1.4 times 10 to the minus 4 in this case. Any questions on that so far? All right. So why is this important for pH? If I wanted to calculate the pH at this point, what thing up here would allow me to do that? The OH minus concentration, right? It won't allow me to get the pH directly, but I could get the POH, right, and then to the pH. So if we wanted that, we do see at equilibrium that the hydroxide concentration is equal to 2 times S. So if we take our value that we got down there, 1.4 to the minus 4 and times it by 2, that would give us a hydroxide concentration of 2.8 times 10 to the minus 4 molar. That will allow us to calculate the POH, which would be minus the log of that guy right there. And if we do that, we end up with like a, on the rounding, like 3.55 as our POH, which if we then subtract from 14, gives us like a 10.45 pH. Again, just taking 14, obviously, minus that number there, right? First off, any questions on that? So again, this is also a very useful aspect of Ksp, is you can actually figure out what the pH of the solution should be or would be if you had something like this. Any questions on that so far? All right, so how does this really impact solubility? Well, let's talk about what would happen if we decided to decrease the pH below 10.45. If I drop the pH below 10.45, what would happen in this case? First off, let's talk about how would I drop the pH below 10.45? Do I need to add an acid or a base? I would need to add an acid. And typically when we add acid, and the way it affects the pH is the acid is adding what to the solution? Yeah, so we have to add an acid, which means we are essentially adding H plus to that reaction. There is clearly no H plus in that reaction, right? But the other thing that's in that reaction is OH minus. So when H plus and OH minus are near each other, what do they make? They do make water. So when we add that acid, you are going to get a reaction of H plus plus OH minus, which is going to make H2O. That is essentially going to do what to this hydroxide? Add more or remove it? It is essentially going to remove it, right? Liquid doesn't affect the equilibrium, right? So it's like reaching in there and taking out the hydroxide. If I reach in there and take out the hydroxide, that would be like removing it. Which way would the equilibrium shift? When you remove, it goes towards it, right? So it would cause this equilibrium to shift to the right. When it shifts to the right, do I have more solid or less solid? I have less, which means it is now going to be more soluble, right? So if I take my guy below 10.45 in terms of the pH, I should actually start to see this guy start to dissolve into the solution, and it will become more soluble in this case. Any questions on that? This is why knowing the pH is kind of important, because you need to have like a baseline of what you need to do, right? Where you need to start, where you need to get it down below to get there. You know, if you were really basic in your solution, like if you're doing a qualitative analysis experiment, you're heavy-handed on the base, right? You may be well above 10.46, and you could add some acid and still be well above 10.46, and you wouldn't see it actually dissolve, right? So this is why, you know, kind of knowing the number is really good. So what happens though, if we kind of do the opposite to that, which is, let's say we take the pH above 10.45. In order to take the pH above 10.45, I need to make it more basic, which means I need to add acid or base. I need to add base. And when we add base, we're adding H plus or OH minus. Yeah, we're basically adding OH minus, which when we now look at this equation, that would be like doing what with the OH minus in this case? It would be like adding more, which means the equilibrium should shift which way? Should shift away from it. It should shift to the right. Or the left. I know you're right, my left. I don't know. It would shift to the left there, which is the reactant side. And that means we should be making actually more solid, which means the solubility of this will start to decrease, right? We will see it shift to the right. I know, left. I know, shift to the left there. It will decrease the solubility in this case. And that is what it means when it says insoluble bases will dissolve in acidic solutions. If you have an insoluble base like this guy right here, and you basically make it pretty acidic, you should start to see it dissolve. And if you make it more basic, it will keep it out of solution. That is why, like in group 2 of qualitative analysis or group 3 of qualitative analysis, they use the same precipitating reagent. The difference between group 2 and group 3 is the acidity of it. In group 2, it is very acidic. In group 3, it's very basic, like we're going to do today. And the reason for that is when you make it really acidic, all those group 3 ions don't like that. They are less soluble and they stay in, I'm sorry, they're more soluble in that case, and they actually will stay in solution. The group 2 guys are less soluble and they'll actually come out of solution in that case. So that's why when you do an experiments like qualitative analysis, we play with the pH a lot. What it does is it allows certain guys to stay in the solution that you want and other ones to be able to precipitate out. And again, if you don't have the right pH, you may not see things precipitate out that should precipitate out. We don't do group 2 anymore, but in group 2, you got to get that pH down to like 0.5 pH, super acidic, to allow everybody to sort of precipitate out really, really well. And again, if you don't get yourself down there, you're going to leave some of those ions still in solution because they will not precipitate out. So pH is a really good way to can affect solubility, and it's really the reason why we do a lot of those crazy steps in qualitative analysis where you read it's like add acid, then add base, and then add acid, and that's all the same sentence, and you do all that. And again, it's just playing with the pH of that solution to keep things in solution that should stay there and allow other things to kind of come out of solution. Any questions on that? So when you have something like this, either an insoluble acid or base, you can actually do the ice table here and sort of the Ksp calculation and figure out the concentration of hydroxide or figure out the concentration of H3O plus, and that will allow you to figure out sort of your baseline pH, and then you'll know, hey, if I go too high or too low, what should happen in that particular case. Any questions on that? Now, a very common question is, will a precipitate form? And we talked a little bit about Q, I think, at the beginning here, but we can use Q, which is like the reaction quotient, to help us determine whether or not we would expect a precipitate to occur. Remember, Q is pretty much calculated exactly like K, so it is products over reactants. So in this application here, it will still just be products, just like our KSP. If the Q is greater than a KSP, we would expect precipitation to occur. If Q is less than the KSP, we would not. Again, if you have it sort of lined up like this, and you remember the equation is pretty much this. If Q is greater than the KSP, going opposite of where the sign is pointing, takes you that way to the solid, so you expect to precipitate. If Q is less than the KSP, going opposite of the side, will take you this way, which are ions, and you would not expect a solid or a precipitate to form. Obviously, if you flip it around, you can go the same way it's pointing, whichever way you want to do that. So let's take a look at one of these here to see how this works and how we can sort of calculate something like this. So if we take a solution that is made by taking sodium hydroxide, 2 milliliters of sodium hydroxide, or 0.2 molar sodium hydroxide, and we add it to 1 liter of 0.1 molar calcium chloride, will a precipitate form? So really the first thing you want to think about is like your solubility rules. So sodium hydroxide is a source of sodium and hydroxide. Calcium chloride is a source of calcium and chloride. So really your one option is the switcheroo, right? So we have calcium hydroxide that could come together, or we can have sodium and chloride kind of come together. We know hopefully from our solubility rules, sodium is soluble in everything, so this is definitely not going to precipitate. So our calcium hydroxide, based on solubility rules, is something that will precipitate. So that is our potential guy that will precipitate. As we super zoom in there. There we go. So looking at those guys, calcium hydroxide is a possibility. So really what we want to compare is the Q value to the KSP value here and see what we are dealing with. So Q is calculated the exact same way. So we would start with our calcium hydroxide, which is really the only possibility here. It would break apart into calcium and a couple of hydroxides here. That means when we go to calculate Q, it would be calculated exactly like the KSP, which would be the concentration of calcium times the concentration of hydroxide. And again, we do need to square it there. Is the concentration of calcium 0.1 molar? The answer is not in this case, because we are putting both of those things together. So we are doing a dilution. So we really need the concentration of calcium and the concentration of hydroxide in the solution when they are poured together. So you could do a little M1V1 equals M2V2 action here. The concentration of calcium would be our calcium chloride, obviously, is the source of it. So we have, what I'm going to do is convert that 1 liter into 1,000 milliliters, same thing, right? So 1,000 milliliters times 0.1 molar divided by our total volume, which is 1,000 milliliters or 1 liter plus 2, basically, right? That's 1,002 milliliters, right, is our total volume when we put both of those guys together. Gives us 1,002 milliliters, allowing our milliliters to cancel here. And we will end up with 1,000 times 0.1 divided by 1,002. Going to give us a calcium concentration of 0.0998 molar. That would be the actual concentration of calcium in the mixture together. Any questions on that? We would do the exact same thing for the hydroxide. This is our source of hydroxide, which is sodium hydroxide. By the way, it's a one-to-one relationship between sodium hydroxide and hydroxide, which is why we could use the 0.2 for both of them. And that's why we could use the 0.1 for the calcium on the bottom there, because again, it's a one-to-one relationship, how they break apart. So for our hydroxide here, it would be our volume of hydroxide, which is 2 milliliters times our molarity of it, divided by the same total volume here, which is 1,002 milliliters. Our milliliters are going to cancel, giving us 2 times 0.2 divided by 1,002. It feels like a lot of 2's in that sentence. That is going to give us, I'll take it to a few digits, 3.99 times 10 to the minus 4 molar. Any questions on how we got both of those there? Now that we actually have the correct concentration of each of those ions in the solution, we could stick it into our Q. So our Q in this case would be our calcium concentration, which is 0.0998 times our hydroxide concentration, which is 3.99 times 10 to the minus 4. We also want to remember we still need to square it. Yeah, so we got to also square that guy. That gets us a little square action there. Maybe try that again. Square it. I don't trust this. I'll type it in. 3.99 minus 4 squared times 0.0998. And we'll go with a 1.6 times 10 to the minus 8. That is our Q value. First off, any questions on how we got to that number there? All right, so in this case, we're going to now compare the Q value to the Ksp value, which is right here. In this case, Q and our Ksp, Q is less than, equal to, or greater than the Ksp. It is less than, right? That means, would we expect a precipitate to form in this case? We would not. Again, opposite of where that points to the product side. Product side is all aqueous ions, so we would not expect a precipitate to form. So even though perhaps solubility rules tells us we should get a precipitate in this case, we will not get a precipitate because it's actually the concentration that's really important here. And we don't have the right concentration to allow the precipitate to form, which is also tying it back to our experiments there with qualitative analysis, why it's really important not to go crazy when you're adding reagents, even though we don't measure out things. Because again, every time you add a reagent to your test tube, you're diluting it, which means you could get yourself to a point at the end of the test where you diluted it way too much and you actually will not see like the final precipitate occur because you actually unintentionally over diluted it and lowered the concentration down. So concentration is like the third thing that's really important for solubility. It can affect it. If you don't have the right concentration of everybody, you may not see the solid form, even though solubility rules say you should see it. So those three things can have a very big effect on the solubility of a substance: the common ion pre and present, the pH of the solution, and the concentration of the ions that are floating around. All three of those things can truly have an effect on solubility and may actually go against what you would think would happen based on solubility rules. So although we are beat into our head sometimes the solubility rules are 100% correct in all situations, it is actually not correct in all situations. Those three factors play a very big role in whether or not you actually see or don't see a solid actually form. Any questions on any of that stuff there?